So I'm reviewing my solution for problem 9, one of the ones that's more of a proof kind of question than, so the question said a numerical answer suffices for 1 to 8, but for 9, the emphasis is on justification as well, okay? So 9 is something, when I look at it, so I did 9, I guess, rather quickly. It gives me a lot of confidence because I know it's there's not much, I guess, complexity to the problem. I know that, the sequence starts at 3. Okay, so you can see my working here is that it starts at 3. So it's defining your sequence, okay? Starts at 3. Next one, the number is sort of a parameter or an unknown, but it's less than 1,000. And so making this a candidate for the questions 1 to 8, I suppose. It's an integer. I guess I implicitly assumed it was positive, even though it probably doesn't have to be. And then the rest of the sequences are defined recursively using this definition. Okay, so you just alternate between adding and subtracting the last 2 terms in the sequence. So then the question is, what is the largest value of b for which 2015 appears in the sequence? So I started by, writing a few of the terms in the sequence. You kind of see pretty quickly, if b is less than 1,000, 2015 is not going to appear there. It's not going to appear there. It's not going to appear there or there. Oh, sorry, that's actually the whole term is a difference. Yeah, so it's going to be too small. B is going to be too small for 2015 to appear in, say, the first 5 terms. Then you could try a random value of b to just get a feel for how the sequence works. You could try a small number. It asks you for the largest value of b, so maybe try a large number that's not really, it doesn't bother you too much. I think 900 didn't bother me too much. So it was pretty obvious after listing a few values that it would get too big. So at some point it would always stay above like 2697. And 2015 didn't appear early on, so it doesn't appear at all. I tried some other random numbers, and similarly 2015 doesn't appear. And so it became apparent that if 2015 doesn't appear early on, or there was there's a window where 2015 has to appear, and then the sequence just gets way too big. So, and if b only, like, the window is determined by the range of values of b, so it's not too big. So I wrote out some values of b again to see where 2015 might appear. It's not going to appear here because 2015 is not divisible by 3. So 5b minus 6 says 2015 plus 6 is 2021 is divisible by 5, which is not the case. But then when you get to 8b minus 9, so b equals 253. So 253 is a value of b for which 2015 appears in the sequence. Okay. So, you could write out the sequence again with 253. And, it certainly works and appears, in the 10th or something term place. And then the question is, why is 253 the largest? Okay. So, you know, short of actually proving it, you could start with a so why is 253 the largest? You know, say you get another B that's bigger than 500. Can you get 2015 in the sequence? Well, if any value of B bigger than 500, say, your sequence of numbers will eventually all be bigger than 5B minus 6, which is already too big. Okay, so if 2015 appears, it has to appear before 5B minus 6, and then we said that 8B minus 9 was the first time, was it 8B minus, yeah, 8B minus 9 was the first time 2015 could appear in any sequence, no matter what the B was. Okay. So here we might have like the idea for a proof. So we can show that, you know, if B is bigger than 253, then so 2015 does not appear at this 8B minus 9 because it's bigger than 253. Only 253 would appear here. And then further than that, it would not appear, and then it would all be too big. Okay, so maybe we could draw a table. So let B be bigger than 253. You know, we have some of the terms in this sequence up to n equals 14. Some reasons why 2015 can't be any of these terms. Okay. It's not quite a proof, but maybe it's the start of an induction. Okay. So let's start an induction. We want to show, say, because 8B minus 9 is the 10th term, we want to, maybe we would just say for all n greater than or equal to, we want to show for all n greater than 11, if B is bigger than 253, then the term in the sequence is bigger than 2015. Alright. So obviously this is not true for less, like the smaller values, because, you know, at the start it starts off low. And we don't have to really, well, we don't need to know that for the smaller values, we just need to know the smaller values are not equal to 2015. Okay, so let's start an induction. So, you know, the table shows that it's true for n equals 12, 13, 14. Okay. And so maybe we could show it's, so if it's true for n plus n, then is it true for n plus 1? Okay, so, okay, I didn't quite write this in there, but say that's n plus, okay, maybe we could assume it's true for n plus, assume for n for true for n and n plus 1, and then prove it's true for n plus 2, okay? But does that work? So for example, you use the, you have to use the recurrence, I feel. Well, not have to, but it's a good place to start, because that's the definition of the sequence. If you're going to prove something general about the sequence, the recurrence is going to be a major character. So, you know, if this is bigger than 2015 and this is bigger than 2015, the sum is definitely bigger than 2015, okay, but the difference might not be. So that's actually a problem, right? And it's a problem probably because it's not true, right? Because when you get to the, you know, the 11th term, it's here, 5B minus 6. 5B minus 6 is less than, it's probably less than 2015. Okay, so 5B is like, oh, sorry, no, we're doing the 12, 13 terms. So this is just bigger than 2015. Yeah, I guess you can't prove 13 is bigger than 2015 using these two, because that one's not. And if you subtract, yeah, if you subtract, it might not work. Okay. But yeah, so what was I doing? So if you want to show it's true for greater than 11, it's true for 12 and 13, and then you want to show it's true for 14. Okay, and 14 is good because it's the sum, okay? But then the next one, 15, will be the difference. Yeah, so if it was already if it started with the difference, and we want to show for equal to 11, oh, it's still okay. I mean, there's some trickiness, because obviously it's not get every third term is not bigger than the previous two, so there's not like some simple argument like that, I don't think. But you can get around this, okay? So, you know, if it is just adding them, then we already have no problem. And if well, if it's not adding them, then n must be odd. Okay, if n is odd, you could just recur it again. If you recur it again, yeah, I guess I'm trying to explain something when I should really just be reviewing what I did. Okay, so if you write it out properly, maybe it looks like this. Assume it's true for k plus 1, k plus 2. Okay, and we want to prove it's true for k plus 3. Okay, and then by induction, it should be true for everything, because we showed it's true for 11, 12, and 13. So, no, 12, 13, 14. So it'll be true for 15, and then 16, and so on. Okay, so k plus 3 by the recurrence is this. If k is nice, so if k is odd, k plus 1 is even, and this is just plus plus, and so it's bigger than 2015, and we're done. If it's not odd, it's even, then we can apply the recurrence again to this to get this plus this, okay? And then this is the same from before. Well, now this plus this will be positive no matter what, because they're the same term, with this one possibly being minus. But this one now, because k is even, is positive 1, and this is bigger than 2015. So by induction, you show that, assuming the 3 previous ones are bigger than 2015, the next one will also be bigger than 2015. Okay, and that's it. So yeah, I guess you just really have to write it out nicely with induction.